So our next speaker is Dr. Erik Schönemann from ESA, and the topic is ESA code bias reference frame. That's pretty interesting and short title. I like it.
Good afternoon. My name is Erik Schönemann. As introduced, thank you for the introduction. I'm giving this presentation on behalf of my colleagues Volker Meyer, Tim Springer, Francesco Cini, and Frank Zimmermann. And the title is not very common, so we talk about reference frames, usually in terms of coordinates. But also here we are using the title because we want to give a frame for the biases to ensure that we have long-term stability. We want to quickly start with an introduction in the topic. So the GNSS environment is changing, as we know. We have an increased number of signals, and in order to ensure the interoperability between the signals, I think it was also obvious in the last presentations, we have to somehow address the challenge of the introduced signal biases. So often referred to as differential code biases. We can also represent them as individual signal biases, but in the end, it's the same. It's just a conversion. So why do we have to estimate these biases? So we have some bias calibrations from the GNSS service providers, but unfortunately not for all satellites, and the biases are also changing over the time. So for example, if the satellite switches from one signal generation chain to another one, or if the biases are recalibrated in the satellite. To overcome this, or to have a long-term stable solution, we have established the so-called ESA code bias reference frame. This solution contains biases, long-term satellite biases, estimates from 2017 onwards. And we have put them in a bias Sinex format, and we use them in our daily routines to stabilize the estimates. The file is also available on our webpage. What is the motivation to look into that? For sure, as I said before, we have to define the datum of the biases to minimize the day-to-day variations. And this is why we have to introduce this, and also in order to make our biases comparable to other analysis centers, in particular also if we have projects where we want to have a combination of biases of different ACs. It's much easier if the biases have the same level and not if you lose a satellite and we have a jump in the combination. So in the beginning, when we talk about setting up or initializing our bias reference frame, we base this on the available calibrations for the satellite. So you use them as an initial starting point, and from them onwards we estimated the biases coming for new satellites upcoming, and also for satellites where we had events. We use the bias file also to monitor the broadcast delays broadcasted by the satellites on a daily basis, so that we have a reference. And we use it also to enable combinations in precise in point positioning, navigation, and timing applications. So for example, our ESA products we are generating today are P1C1 products, but if we look at what is available on Sentinel satellites, we have to convert the observations to make use of our products. The same applies actually for the phase bias products. So here we have to apply the code biases to the observations before. So in the end, we can process the ionosphere free linear combination, assuming that the satellite biases are equal to 0. How do we treat, or everybody knows that there are different signal components. So we have on at least modern GNSS, we have pilot and data signals, and we have the possibility that the receivers track the signal in a different way. So for example, a mixture of pilot and code signal, and reports them as X component. When we now estimate these biases or want to provide them, we have to discuss we have to think about how to optimally estimate these biases. Do we have to do it for pilot, for data channel, and for the mixed signal, which makes it difficult because in the end, in particular, the mixed signal is not provided by all receiver types. So we have it for some, it's a limited network, and it may change over the time. So we analyzed the differences between the different components, and what we have shown so far was, or what we found out, is that in the end we can assume that the biases for all the components we have can actually treat it in the same way, at least at the accuracy level we have at the moment. So looking at the Linux code displayed on the right side, for example, for Galileo, for L1 and L6, we have B, C, and X components, and we just treat it as C component. How do we generate the bias reference frame? So as usual, as done also by all the analysis centers, we start with the estimation of a global ionosphere model. In the first place, using one signal combination. And then in the second step, we generate differential code biases, fixing the ionosphere for all other possible signal combinations. The next step is then a long-term stacking. So we stack it over the entire period where the DCBs are stable, where no event occurred. But we have to make sure that we automatically detect any changes, in particular in close to real time, so that we can adjust it in the bias reference frame. And the final step for the bias reference frame is the merge of all differential code bias in a single Sinex file. And we add the C1C, C1W code bias at the end. I will come back to this in one of the next slides. This just gives a preview of the file we have provided, or we provide via our web page, and you can download it from the link you see. Coming back to the P1C1 correction, using the BREF, I've started using our own corrections in September last year to also reduce the external dependencies on other products. So if we generate the bias ourselves, it makes sense that we use it. And we compute it out of the BREF, the bias reference frame, by subtracting the C1C, C2W bias from the C1W minus C2W bias. And this is where we get the C1C, C1W bias. We can see it on the right-hand side on the graphic. These are the green dots. These are all the biases we generated out of the bias reference frame. But we also see the offset compared to the code biases, the monthly code biases shown in yellow. And this we solved by putting a zero mean condition on the biases. So we adjusted the global level, and then we see that we end up quite nicely at the same level as the code biases. When we compare code and hours, we see that we have more points for code, but this is because it's monthly values and we have only one value. We keep a stable value over the entire time. So when looking at our solution, we see that the clock is slightly increased, but the standard deviation decreased, which shows that the clocks are more stable. How do we treat code bias jumps? So as mentioned before, code bias jumps, in particular if we constrain the values out of the BREF, this is an issue because if we are not detecting them, we introduce errors in the solution. So we have to detect them. What we see here are differential code biases for Galileo over the entire period from 2021 to up to now. On the bottom left, we see C1P, C5P. On the top right, we see C1C, C5Q. And the bottom right, we see C1C, C6C. Maybe only looking at the top right plot, we see the biases for the different satellites with different colors, shown with different colors. And we see that adjustment of the DCBs took place around. Okay, in 2021, the bias of the Galileo satellites have been adjusted, as we see on the right-hand side, on the top right. So we see the colors on the bottom, and we see that the bias have to be adjusted and are now close to zero. And these kind of jumps we have to detect and correct in the bias reference file. Coming to the last part of the presentation, the phase biases. We generate phase bias since many years, so for GPS, Galileo, Beta, and QZSS. But also here we have to make sure that the phase bias are working with the frequencies we are having on the satellites, for example. And we have done this in the past also for C1, which we have corrected, where we just corrected the observations to fit with the phase bias, with the observations used for the phase bias, and we can do the same also for C2. When we do this, we see now when we apply the bias, if we don't apply the bias, so what we see on the left-hand side is the numbers of fixed, or the percentage of fixed ambiguities for the sentinel when using the code bias. We see it's the lower curve in blue. We are around 98% in fixing the ambiguities, and if we properly apply, or if we correct the observations to be aligned to the observation tab we have used to generate the phase bias, we end up with above 99% in fixed ambiguities. We can see the same on the right-hand side when we look at the residual plots. We see on the top the two colors on the top, the green and red, are the code residuals before or without applying the bias in green. And when we apply the bias, we see that the code residuals also significantly reduce. This is the red, these are the red dots. And the same for the phase, where we have blue without bias applied and orange when we apply the bias. What do we do in future? So we plan to enhance a bit the BREF we have at the moment to also come up in the end with OSPs. We will also start a bit earlier with the generation, so we will generate a global GNSS solution, including orbits, clocks, and the reference frame. We use the OSP BREF, which we get out of the processing at the end, and also in the further processing, estimating the ionosphere model. Then we generate again, as done in the previous step, or as done also today, the DCBs for all different signal combinations. We perform the long-term staking of the DCBs. We will merge all DCBs in one single bias file and add the C1C, C2W again. And finally, we will convert all these DCBs to OSPs and provide a fully consistent set of biases for each constellation. This is the plan we have, so this should come soon. So in conclusion, we maintain this long-term differential code bias product, which will become OSP product very soon. The product, the BREF as it is at the moment, is available on our webpage. We also generate a phase bias for all GNSS except for cloners because of the FDMA. This is what we don't do. We are not publishing them yet, but something we are thinking about, in particular when we have the new setup. So we have to prepare the new setup first, and then we can think about publishing also the phase biases. Our code and phase bias products are state-of-the-art, and the BREF, which we are currently generating, contains only DSP, but we will generate and maintain an OSP version very soon. Yes, and consistent with also our phase biases. With this, I thank you for your attention, and I hope with the outage I did not take too long. Thank you very much.